So let's see if I managed to lose my stylus. No, I didn't. Okay. I will. I can do it a little bit. Because I can auto hide that. That's a little bit better, eh? Yeah, it makes a difference. And maybe I can darken the wall, darken those windows. Okay, so it started out by talking about stray capacitances and just capacitance. And so our scope probes are 3 feet long. That's why it says that in the textbook. And so this is our first detailed look at a coax cable. And so there's a central conductor, some dielectric, which is usually Teflon, that whitish looking stuff. And then there's the braid and then the outer insulation. And the dielectric is there, the medium that is there to keep the center conductor centered. You want to keep a reasonably constant distance. The capacitance is parasitic. You don't really like that the coax is got a capacitance, but at the same time you want to be shielded and you want to know that what the capacitance is. And they quote it as something per foot, and that's why he mentions 3 feet being important. But tends to happen over long distances of coax that this pretty square wave you put in starts looking like this. Or that's pretty extreme because of the RC. You got a rise time and a decay time. And the solution to this is to actually use wider coax cable. So the coax cables of your probes are quite small. You'll see up there some coax cable about 1/4 inch in diameter. That's actually called thin coax. The coax they used in the beginning with the Ethernet was so-called thick coax. It was like 3/4 of an inch in diameter because if you recall from Physics 2100, even in this class, capacitance is area over separation. So the separation is in here. So if you think about it, these are two parallel conducting plates being coaxial like that. And then, so the dielectric medium is chosen to have a low dielectric constant, not a high one. And then, even a bare wire, so if you were to look inside your oscilloscope, at some point you can't have a shielded cable everywhere. Although really high frequency oscilloscopes, they go beyond cables. And if you looked inside a really expensive one, the wires are actually tubes. They're waveguides. I don't know if you guys have taken E&M, like junior or senior level E&M. You're going to learn about waveguides and transverse electric modes and transverse magnetic. Any of it sound familiar? If you look at a cell phone tower, there's these looks like cables running up the side, right? They're actually hollow metal tubes. And because at 2.4 gigahertz, coax cable is good to about 300 megahertz. So above that, you can't propagate the signal efficiently. So you end up using something that doesn't have any center conductor. But that's another discussion. But if I have a bare wire, even a bare wire, like that's one of the reasons I pushed you to move away from those adapters with the BNC adapters and the banana cables, because a bare wire has a capacitance. Even though there's no other wire or conducting plane, there is effectively one because it's like sort of like it's an impedance, isn't it? Sort of like an impedance. But there's a capacitance of any bare wire. or two wires next to each other. This is something people deal with when you design circuit boards. You have a 2.4 gigahertz Pentium chip. Well, now they're i5s and i7s. It turns out that the size of the traces on the circuit board are determined, they're waveguides themselves. All the signal travels on the outside. That's why the waveguides you see are hollow, because none of the, if you'll learn in E&M about skin depth. Even at 60 hertz, even though they run those wires that hang from the big steel towers, they're an inch in diameter, and they go up to 1,000,000 volts. They're not any bigger because even at 60 hertz, once you make it to an inch in diameter, there's no current in the middle because of the skin depth. You'll learn about that in E&M. For us, it's about the capacitance, the stray capacitance, and you notice that if we get up into 1 megahertz, we're already loading down our system because the I should have brought the picture of the basic input. Let's see what we have on this slide. So what we normally would have is just the input into the oscilloscope, and it's across the 1 mega ohm. So this is the same picture. And then there's the capacitance of the cable, and then there's some stray capacitance in here because there's the bare wires inside there. And yes, it does have a metal box around it to tend to shield it. So we try to overcome that by making the 10 times probe. So this is a naive 10 times probe. And it's naive because it doesn't address the stray capacitance. In fact, we've exacerbated it because remember the rule of thumb. And the rule of thumb says that for parallel circuits, the low Z dominates. So if I merely increase the ohmic load instead of 1 mega ohm, making it 10 mega ohms, I made the problem even worse. So the solution is to make a voltage divider that's both, because of course the 9 mega ohm and the 1 mega ohm is a voltage divider, right? So we're dividing the voltage by 10, and that's why it says, even though it's 9 and 1, remember it's going to be 1 over 9 plus 1. So that gets you a 1/10 step down. Notice on your oscilloscopes, there's the one-time probe, and then if you look to the right clockwise, there's a 10 times probe numbers. Right? So you have to watch out for that. So then what we do is we form a voltage divider with two capacitors so that no matter what current, what frequency we're at, we still get the 10-to-1 reduction. Now notice that the reactance is 1 over 2 pi Fc, and that's why it's a way to remember. I have 9 and 1, but here I have 11 and 100. And that has to do with the 1 over 2 pi. So we still have the chi c plus 9 times chi c plus chi c. It still equals 1/10. but then the values are the inverse. So the smaller capacitor is here, and the lower capacitance. So the thing is that since it's a stray capacitance, just like a stray dog, you don't know exactly its behavior or its value. And that's why you see this little arrow through the capacitor symbol. That just means it's an adjustable capacitance. So you could, it's like a potentiometer, something like that. Although what happens is usually when it's a potentiometer, they draw it like this because that is usually a 3-terminal device, whereas an adjustable capacitor is a 2-terminal device. That's not super important, but it fills in. We always like to weave a whole cloth. So then we see now if with the adjustment here, notice that the x-axis is frequency. Notice that he's already saying that we're going to see problems at 10K and 100K. The values we've been using have been picked carefully to avoid problems. But we're going to be now, when we start dealing with transistors, we're going to have to deal with very low impedances. And we want to have our input impedance or higher impedances. We want our input impedance of our scope to be as high as we possibly can get it. So if we were to input a square wave, it may not be, but it's right out of the textbook. If the capacitor is off, either way, overstate the high frequencies or the low frequencies. Remember, as a square wave, the high frequencies are represented by the leading edge of the square wave. Remember your Fourier transform. And again, I'll post these if you want to just pick and choose to print and pay and print them out and paste them in your book. That's fine. You can make or you can make a sketch and then paste it right over your sketch. Right there, you go. That's right. It's in the scope probe. I'm going to show you in a moment. Yep, good question. The adjustable, and in some of them, it's in the probe. Some of them are in the actual the box that's connected to the oscilloscope. The black ones are in the probe itself. The gray ones is a general rule. I'll show you. Don't worry. Let's see what's on the next slide. Oh, and this is very similar to one of the homework problems. So notice that since we're assuming that the compensation capacitor is unknown, or we assume that we don't know the V out over V in for both of them, or well, we know for the resistors for sure it's V over 10. So we have to draw the equivalent circuit as the center. But what we want is we want the Thevenin voltage for both of them to be V over 10. And then if we do that, then we can change it over to the picture on the right. Just stare at it for a minute. If this guy is in fact V over 10, if they're both V over 10, there's nothing wrong with replacing it with one of them that feeds into both components. So this is, again, a Thevenin decomposition of the proposed scope probe, the compensated probe. And that's what C comp is compensated. Okay, so all oscilloscopes, all decent oscilloscopes, have a special output. So here, it's right here. It's a little hard to see there. So look for, some of them it's a receptacle. Some of them there's a little piece of metal sticking out with a hole in it. Here's another one. Let's see where this one is. And oh, here it is in the lower left. And in this case, it's a loop, and you're able to hook the scope probe to it. This one's on the lower right, but I do know that some of them have it. I know some of you have one that is the older. Whoops. So right here in this stack here, there's a little hole. You can take your probe, your scope probe, and you can pull off the end of it, which is useful sometimes when you're troubleshooting. So that's the hook thing, and some of them unscrew. So I don't think any of you have one that unscrew, the older ones. But this is nice when you're testing a circuit. And if you happen to have an oscilloscope that only just has a little hole, you can push it in. But just be careful not to torque it around. So the black ones have a little opening in the side. Well, make a liar out of me. No, this one apparently does not. So anyways, some of them have an opening in the side, but most of them, if you look at the place that plugs in, you'll see a little hole in the side of it. Now, there's a variety of screwdrivers on the table there. Yeah, this one here will accept a slotted screwdriver. And what you do is, now I don't have, well, maybe, let's take a look here. Well, this thing, I have never done a probe compensation on this. I better learn how. So what you do is you connect your scope probe, put it in 10 times, and connect it to that output. It should be a 1 kilohertz square wave. And you twist that screw until you get a beautiful looking square wave. So let's all do that. I'm going to pause the recording. And in fact, it's already 20 minutes long. I'm going to stop it and I'll restart a new recording.